Today we're explaining diffusion models, the mathematical nightmare that powers DALL-E, Midjourney, and every AI art generator that's about to replace human creativity with statistical noise. Not the clean denoising process from research papers, but the real implementation where your GPU farm catches fire generating furry art, your loss function explodes into neon hell, and you realize you've accidentally built a hallucination engine using nothing but Gaussian noise and stolen Instagram photos. 3 AI engineers, 1 computer vision researcher who's lost faith in pixels, and 45 minutes of pure generative horror. I'm Sam, and someone's definitely getting sued for copyright infringement.
I spent 2 years implementing diffusion models from scratch. 2 years. The papers make it sound elegant, progressive denoising, score-based generative modeling, reverse diffusion process. Reality. I debugged for 6 months because my noise scheduler was backwards. The model was adding noise instead of removing it. It was generating pure static, but the loss was decreasing. I thought I'd discovered a new form of abstract art. Turns out I just implemented entropy maximization.
My job is scaling these visual hallucination engines. You know what happens when you try to generate a 1024x1024 image with a diffusion model? 50 denoising steps, each requiring a full unit forward pass. That's 50 expensive neural network evaluations per image. Our GPU cluster generates heat equivalent to a small steel foundry, all to create anime girls with too many fingers.
I built the systems that artists use to generate images. The dirty secret? These models don't understand what they're creating. They learn to remove noise in a way that statistically resembles human art. It's like teaching someone to paint by showing them a billion photos being slowly dissolved in acid, then asking them to reverse the process. The fact that it works at all is terrifying.
Dr. Vasquez, you're our guide through this pixel purgatory. Jordan and Zoe, prepare to explain why adding noise became the path to artificial creativity. No mercy, no hand-waving about learned priors.
Let's start with the fundamental question: what is a diffusion model?
It's a generative model that learns to reverse a noise process. You start with an image, gradually add Gaussian noise until it's pure static, then train a neural network to reverse that process.
That's the marketing pitch. What's actually happening mathematically?
Score matching on a noise-corrupted data distribution. You're training a neural network to predict the gradient of the log probability density function at each noise level. It's learning the score, which direction to move in pixel space to make an image more likely under the training distribution.
Better, now explain this forward diffusion process everyone talks about.
You take a clean image and progressively add Gaussian noise over t time steps. At each step t, you add noise according to a schedule, usually. After enough steps, your image becomes indistinguishable from pure noise. It's like watching a photograph dissolve in acid, but mathematically controlled.
Show me the math. How do you define this forward process?
Oh fuck, qxt xd1 equals nxt. Square root 1 xd1, at each time step you're sampling from a Gaussian centered on a scaled version of the previous image. The magic is that you can skip to any time step directly. qxt x0 equals nxt. Square root alpha t x0 1 alpha t where is the cumulative product of 1.
What's the reverse process trying to learn?
P theta xd1, the probability of the previous, less noisy image given the current noisy one. But you can't compute this directly, so you approximate it with a neural network that predicts the noise that was added, then subtract it.
Why predict the noise instead of predicting the clean image directly?
Training stability. Predicting the noise is easier than predicting the final image, especially at high noise levels. Plus, the noise prediction connects to the score function. You're essentially learning x log pxt, which tells you how to denoise optimally.
What neural network architecture do you use for this noise prediction?
UNet, same architecture used for image segmentation, but modified for denoising. It has skip connections that preserve fine details, downsampling to capture global structure, and upsampling to reconstruct the output. The time step is embedded and injected at multiple layers, so the network knows how much noise to remove.
How many parameters are we talking about?
DALL-E 2's UNet has around 1.5 billion parameters. Stable Diffusion uses about 860 million, and you need to run this network 50 plus times per image during inference. Each generation is like running a medium-sized language model dozens of times.
Now the interesting part: how do you condition these models on text prompts?
Cross-attention. You encode the text prompt with something like clip or T5, then inject those text embeddings into the UNet via attention layers. The model learns to attend to relevant parts of the text when denoising different regions of the image.
What's Clip doing in this pipeline?
Clip learned to match images and text in a shared embedding space. It's the bridge between language and vision. When you say a red car, Clip provides embeddings that the diffusion model can use to guide generation toward images that look like what Clip thinks a red car should look like.
How was Clip trained? What's the data set?
400 million image text pairs scraped from the internet. Alt text, captions, basically any text that appeared near images online. It's the digital equivalent of showing someone every photo and caption that ever existed, then asking them to learn what words mean.
What about the training process for diffusion models? How do you actually train this?
Simple loss function but computationally brutal. For each training image, you sample a random time step t, add noise according to the forward process, then train the UNet to predict the noise you added. It's just L2 loss between predicted and actual noise, but you need to do this for billions of images at thousands of time steps.
What's the training data? How much visual information are we processing?
LAION5B dataset 5 billion image text pairs. That's like every photo on Instagram, Facebook, and Flickr combined. Stable Diffusion was trained on a subset of 2 billion images. We're talking about most of human visual culture scraped from the internet.
Training cost.
DALL-E 2 training probably cost $10, $20 million in compute. Stable Diffusion was around $600,000 thanks to more efficient training. But that's before you factor in data collection, cleaning, the army of researchers. These are some of the most expensive art projects in human history.
A terrifying question, what happens during inference? How does noise become art?
You start with pure noise and run the reverse process. At each time step, the UNet predicts what noise to remove, you subtract it, add a tiny bit of random noise for diversity, then repeat. After 50 steps, noise becomes a coherent image. It's like watching static on a TV slowly resolve into a painting.
Why do you need so many denoising steps? Can't you just jump directly to the final image?
The reverse process is only approximate. Each step introduces small errors. Take too big a step and you get artifacts, blurring, or complete garbage. It's like trying to reconstruct a shredded document. You need to piece it together gradually, not all at once.
What's the biggest failure mode of diffusion models?
Hands, fucking hands. The model learned that humans have hand-shaped appendages at the end of their arms, but it never learned the constraint that hands have exactly 5 fingers. You get Eldritch horror hands with 3 to 8 fingers in impossible configurations.
Why can't they count fingers?
Because they're not counting, they're pattern matching on pixel correlations. A hand is just a blob of skin-colored pixels with some finger-shaped protrusions. The model learned the texture and rough shape but not the structural constraints. It's like an alien trying to draw humans based on blurry photos.
What about text and images?
Gibberish. The model learned that signs have squiggly marks that look like text, but it never learned language. You get text-shaped noise that looks like words from a distance but dissolves into meaningless symbols up close.
How do you solve these problems?
Better training data, specialized architectures, post-processing. Some models now use separate networks for hands and faces. Others use iterative refinement. But fundamentally, you're fighting the statistical nature of these models. They want to generate average hands, not correct hands.
Holy shit, so we've built visual hallucination engines using stolen internet photos. They can't count to 5, and we're using them to replace human artists. This is fine, totally fine.
Welcome to the age of artificial creativity. We've democratized art generation, but nobody knows what the machine is actually learning from our visual culture.
This episode brought to you by Engineer Panic, where we reveal that your AI art generator is just very expensive pattern matching, because understanding the difference between creativity and statistics is probably important. We're back, let's talk about the practical nightmare of actually deploying these visual hallucination engines. Jordan, what's the infrastructure reality?
Compute hell. Each image takes 50 unit forward passes on a GPU that costs $40,000. Generation time is 10 to 30 seconds per image. Scaling to thousands of users means GPU farms that consume more power than small towns. We're burning rainforests to generate anime waifus.
And then there's the content moderation nightmare. Users constantly try to generate NSFW content, copyrighted characters, deepfakes of real people. You need safety classifiers, prompt filtering, image analysis. The safety systems are sometimes more complex than the generation models.
Don't forget prompt engineering. Users think they're being creative, but they're really just learning to speak in the statistical language the model understands. Trending on ArtStation became a magic phrase because the model learned to associate it with high-quality art.
What about the copyright shitstorm? Are we in legal trouble?
Oh, absolutely. The model was trained on billions of copyrighted images without permission. Artists are suing, stock photo companies are suing, everyone's suing. The legal landscape is a fucking minefield, and we're all just hoping fair use applies to statistical pattern matching.
Plus, the model can reproduce copyrighted characters if you prompt it right. Disney lawyers are probably sharpening their knives as we speak. We built a machine that can potentially infringe on every piece of visual IP that ever existed.
The ethics get weirder. The model learned artistic styles from dead artists who never consented to their work being used. We're essentially creating zombie artists that can paint in Van Gogh's style forever.
What keeps you up at night about diffusion models?
Deepfakes. These models are getting good enough to generate convincing photos of real people. We're one breakthrough away from completely destroying the concept of photographic evidence. Reality is about to become negotiable.
The death of visual truth. When anyone can generate photorealistic images of anything, how do we distinguish reality from AI-generated content? We're teaching machines to lie with pixels, and they're getting really good at it.
That we've built a system that can manipulate human perception at scale. These models don't just generate images, they shape how we see the world. They're learning our visual biases and amplifying them back at us.
Any advice for engineers working with diffusion models?
Start small, understand the math, and prepare for GPU bills that make you question your life choices. Learn to debug noise schedules, attention maps, and why your model generates six-legged cats. Also, invest in good cooling systems.
Build robust safety systems from day one. Content moderation, copyright detection, deepfake prevention, these aren't afterthoughts. Also, learn to explain to users why their prompts don't work the way they think they should.
Remember, these are tools, not magic. They're incredibly sophisticated, but they're still pattern matching machines trained on human visual culture. Question their outputs, understand their limitations, and maybe don't use them to generate evidence in court cases.
This has been Engineer Panic. We've learned that diffusion models are noise-to-art converters that can't count fingers. Nobody understands how they work, and we're using them to redefine reality anyway. Sweet dreams.
Thanks for the existential crisis about visual truth. Now I'm going back to debugging why our model thinks every human has Eldritch horror hands.
And I need to explain to our legal team why our creative tool can accidentally generate copyrighted characters when users type the wrong magic words.
Keep building, keep questioning, keep panicking. The future of visual media depends on engineers who understand both the power and peril of statistical creativity.
This has been Engineer Panic, where diffusion models meet mathematical trauma and legal nightmares. Until next time, remember, every pixel is a hallucination, but some hallucinations are more expensive than others.